Hello again, friends. In this video, we're going to be trying to find the volume of a shape that's created when we rotate a region that's between either two curves or between a curve and an axis. We rotate that region around the x-axis, and we're going to be trying to find the volume of that shape using cylindrical shells. So to get us started, I've got a problem down here for us to work on, and we have the function y equals 5x minus x squared, and that is this guy right here, and then we have y equals x, and that's our beautiful diagonal going across right here. So like I said, what we're going to be doing is we're going to be rotating around, oops, it's supposed to be y-axis, I forgot to change it from the last video. When we rotate this around our y-axis, right, well, we see that what we're going to get is we're going to get another diagonal right here, which that is not very diagonal, but bear with me. And we're going to get our wing shape up here. So once we rotate that around, we're going to get something kind of like that. Now, like I said, what we're going to be doing is we're going to be finding the volume that's created. So when we rotate this around, what we're really getting is we're going to be kind of getting this cone shape, right? Because this is going to make a cone. So it's going to be a nice, beautiful cone for us to see that we're working with. And then we're going to have this kind of like, it's going to kind of like dip down on the inside, right? So we're going to have this like other kind of cone on the inside, because all of this is going to kind of curve into it. So we're going to have this like empty cone in here. Like that's right here, right? So that's kind of hopefully a little better visualization, more 3D. Wasn't very great, but anyways, so that's what we're going to be trying to find the volume of that like vase shape. So in order to do that, like I said, we're using cylindrical shells. And one thing we have to kind of keep in mind when you're using cylindrical shells is the equation that we're going to be working with, which to find the volume, we're going to be using this equation right here. You can see that what we have in here, right here, this, what it looks like, is a part of the equation for the surface area of a cylinder. So instead of cylindrical shells, maybe you could think more of like cylindrical surface area. It's not all of the equation for the surface area, but it's part of it. And you can see that because if we rotate right here, and we're going to get a cylinder, right? So if this is our cylinder, it has a radius r, right? That's our radius. And then this part is the circumference of a circle, right? So that's going to tell us the measure of this around the top here, right? And then our L tells us our length of our cylinder. So we see that if we were to like kind of cut this down the one side, right? What we're really going to get is we're going to get this really long rectangle, right? It's going to have a length L, and then this, if we were to cut this right here and down here, right? This all the way around is our 2 pi r. That's this across the top here, right? So what we're really getting is we're multiplying, right, some length times a width. We're getting an area of like these rectangles, right? So that's kind of what this is telling us, is we're going to be finding the area, or the surface area, so to speak, not completely, but of these rectangles that are going to be kind of embedded within our figure. And we're going to be finding the volume of those, and with that we're going to be able to find the volume of our entire shape that's rotated around the region, or that's rotated around our y-axis, excuse me. So to get us started, I'm going to get rid of all of this for us here, and we're going to take a look. I'm going to blow up our picture here so you can get a better kind of feel of how these cylinders fit inside our graph here. So I guess I'm going to draw them a little bit bigger. So we have our diagonal, and a diagonal over here, right? And then we have our curve, kind of like this, and our curve over here, kind of like this. A little rough, but it'll get the job done. So what we did in our work before, right, is we would take, if we're trying to find like the volume using either the disc method or the washer method, right, we take a rectangle within our region, and we'd give it a width dx or dy. Now the difference here is what we did before in the disc and washer method, right? Is all of our rectangles were perpendicular to our axis of rotation, right? We're rotating around the y-axis. Our rectangles were all perpendicular. So they'd all go like this. They're all this way, right? With respect to our axis. With cylindrical shells, our rectangles are going to be parallel to the axis of rotation. And because of that, what the width of this rectangle is, right? If we were to draw, like, if, you know, it's an infinitely small width, but if we were to kind of graph it out, right, this is our x-axis, so he has some width in terms of x, so that's where we get our dx from. We're going to be integrating with in terms of dx, even though we're rotating around the y-axis. So it's one difference you have to keep in mind when we're integrating later, that although we're working with our y-axis, because we're using cylindrical shells, we're integrating in terms of x. So like I said, we have a parallel rectangle within our region, and when we rotate our region right here around our y-axis, right, this rectangle is going to be rotated around too. So this rectangle over here is also going to be graphed over here on this part, right? And he's going to be rotated all the way around. So he exists all the way around this, the figure that we're going to have, right? That weird vase shape, he's going to be all the way around. And we see that this rectangle now, he's made our cylinder, right? So now that we have our cylinder within our figure, what we have to do is we have to figure out, right, what there's going to be like infinitely small cylinders within our shape here, right? So we have to figure out the radius and the length of our cylinder, plug it into our equation, and within our bounds we can then find the volume of the entire shape using all of these, like, this infinitely many number of cylinders within our shape. So what is our first question we have to ask ourselves is, what is our radius, right? Our radius goes from our axis out to our rectangle. Same thing down here, right? Our radius is going to go from here out to our rectangle. So we see it touches both of our functions, but more specifically, it touches both of our functions at the same x value, right? Our radius then, like we see, is some distance x, right? When whatever x value we plug in within our bounds, that's going to be our radius, right? So if we have, for example, a smaller cylinder, I'm going to try to draw a smaller cylinder down here, for example. Right, go here from here. He's going to rotate all the way around. Right. Our radius is going to go from our axis, it's kind of poorly drawn, but to our function, from our axis to our function down here, and once again, it's going to be some x value, right? Just a smaller one. So our radius changes throughout our entire shape. If we go all the way out here, we're going to have a radius that's longer, but it's going to be within our bounds from 0 to 4, and it's going to be whatever x value we're working with within our bounds. So for our radius, we're going to plug in, oh, my bad. We're going to have our radius be x. So we have our radius. Now I have to figure out what the length of our cylinders are, right? So our length of our cylinders is determined, right, by this right here. This is our length. And what we see is it's defined from the top of this curve to this curve, right? So if we, for example, before, like if we consider back to our washer method and our disc method, right? If we wanted to consider just the length from the x-axis up to this curve, it'd be this entire distance right here, right? Can you see that? Yeah, okay. But we don't want the entire length from this curve to here. So what we have to do is we have to subtract out the length from this bottom curve, right, our y equals x, to the y-axis. So we're going to subtract out the distance between this curve and here. And that's going to get us just the length within our two curves. So, and because our curves change throughout, right, our lengths are going to be different throughout. So, like down here, right, if we measure from here to here, the length from our curve y equals 5x minus x squared, and then we subtract out the length from y equals x, right, we get what just left what we want in the middle. But like I said, our curves change throughout, our lengths are going to change throughout. So in order to determine our length, what we have to do is we have to plug in our curves. So we're going to plug in our top curve, just like we did with like the washer method before, right? You plug in whatever's on top, and then you're going to subtract out whatever's on the bottom. So that's our curve y equals x. So that is going to tell us the length of all of the cylinders within our figure that we have. So we know our radius is in terms of whatever x value we're working with. Our length is going to be in terms of whatever the difference of our two functions are at that point x, right? So whatever point x we're working with, whatever the distance between the two functions are at that point x, that's going to tell us our length. And now that we know those two things, we can plug them into our integral, and we can actually solve for our volume. So I'm going to get rid of our graph here. And I'm going to erase this. And I'm going to rewrite it, and now we can actually take our integral. So once again, we know our bounds. If in terms of x, we're going from 0 to 4, right, because that's where these guys meet. It's at 4, 4. And then we're going 2 pi times our radius, which you said is just in terms of x, times our length, which we know is going to be our 5x minus x squared minus our x dx. So now that we have that, we can actually, we're going to simplify. So we're going to get from 0 to 4, 2 pi, multiplying our x through. What we're going to get is, we're going to get a nice, before I get started with that, I'm going to pull my 2 pi out, just because he's just going to follow us all the way through. So now I'm going to FOIL my x through, so we're going to have 5x squared minus x cubed minus x squared dx. Once again simplifying, we're going to have 0 to 4, we're going to have 4x squared, right, because these two guys are going to subtract, minus our x cubed dx. So now that we have everything nicely simplified, we are going to integrate. So our 2 pi is going to follow us. The integration, when we integrate this, right, we're going to get x squared. We have x squared, we're going to get x cubed, and we're going to multiply by our reciprocal. So we're going to get 4 over 3. Now we're going to subtract out, we're going to add to our exponent. We're going to get x to the 4th, multiply by our reciprocal of 1/4. And we're going to evaluate that within our bounds of 0 to 4. Now when we do that, we plug in our 4, we plug in our 0, subtract the 2 out, right? We're going to get a grand total of, and multiply our 2 pi in, right? So, well, I'll write that out. So we're going to do 2 pi times, we're going to have 4 over 3 times 4 cubed minus 1/4 times 4 to the 4. When we plug in 0, we're just going to get minus a 0. So, now that we have that, our grand total will be, once we evaluate what this is, we're going to get a 128 over 3 pi. And that will be our answer for our volume of this region when we rotate it around the shape that we get when we rotate this region around the y-axis, and we found that volume using cylindrical shells.